Hey folks, in this video I want to walk through an implementation of a linear probing hash table. So let's take a look. We have basically the code from the book. As a note here, the book uses parallel arrays. Parallel arrays are not good. I already went on a rant in a different video, right, in the symbol tables module about this. Parallel arrays are horrible. You don't want to waste your time having to maintain two arrays at the same time when you really can just have one array that contains an object of two things. So, that is already dumb. I won't talk about it anymore. All right, take a look at the code. You can kind of know, what to expect to see. Hopefully, right, the mechanisms we see in the code kind of align with the things we were demoing in the previous videos. All right, so have, of course, our linear probing hash table, ST, right, name of our class, has two generics, pretty much as we expect. Also, as we expect, we have N and M, right, the number of things in there, the size of the array. All right, then we have basically our two arrays, right? So we have an array basically of keys and an array of values. And they'll be in step, right? So that, if I have to add a key value pair, it's like, well, I'll add the key to index 10, I'll add the value to index 10 as well. So I'll always change them at the same time. A little bit of code duplication. All right, so I have my two things there, right? Those are my two M size arrays. Now what happens? I have my two constructors. And my two constructors, well, let's see. Looking at the default constructor, and this is a question for you guys, does the default constructor look right? So no, right? Something's horribly wrong. We're using the power 2 number there, right? So that's not acceptable. So no power 2s, right? No power 10s. This should probably be something like the other example we had where it was like 997, right? Just some large prime, right? Hopefully the number is large enough that it's something that we don't have to worry about resizing later or anything like that. Just make it prime, make it reasonably large. All right. So the next thing we have in here is basically the linear probing hash ST. So what do we have? We have these three lines here. Initially, what we want to do is basically store M, right? Our size of our array, right? How many slots we're going to have in it. So we store that, and then we create, right? There are two different arrays, right? So we create an array of keys, array of values. They're the same size, right? They're in parallel, and they're both on size M, right? Because that's, size M is basically going to be your, number of elements, right? It's the number of things you could store, right? And both arrays have to be that same size. All right, so that's reasonably straightforward. This is literally just the same thing from the previous hash table example. This is just hash again, right, where it takes the code, and from that, does some magic and gets back out of index, right? So that's, kind of, we've already seen that stuff. Okay, so hopefully this stuff isn't too bad. Let's take a look at some much more complicated things. So we're going to take a look first at put. So put is kind of the most complicated one here. So what's going on here, right? So put basically, right, is going to start by saying, do we have space to add an element? Because there was that constraint earlier where we said, oh, hey, M needs to be at least N, right? Otherwise, I run out of spaces, I won't be able to add things, stuff will break. So the first thing I do is basically check to see whether my array is large enough. And so I check to see basically is N greater than or larger than, or greater than or equal to half of M, right? So we actually want this relationship here where N basically should be no more than half of M, right? So M should be at least double N, right, at all times. And the reason we want to do that is so that we can have good performance. By the way, this ratio here, N divided by M, we call this a load factor. So a load factor is basically telling us, the relative proportion of, empty slots to used slots in an array. And ideally what we want is we want our load factor to be around 0.5. That'll give us our O of 1 time that we're really looking for, right? We want to get down to constant time. If we let this get too high, right? If we let all of a sudden, we have 99 elements in 100 in an array that has space for 100, then our performance will degrade. Well, then our performance will go down, and we'll get something that's like O of N or something like that. So yeah, first step is basically make sure our array is large enough. Okay, so now the actual code. So first of all, we created a variable called int. Notice it's something we're going to use in the inside of the loop. The reason why it's being created outside is so that we can use it. Notice that I is being created outside of the loop. The reason for that is that we can actually use it after the loop instead of it going away. Because normally, right, when you create a variable inside of a loop, it just exists in the lifetime of the loop. Once the loop exits out, it goes away. Here, though, what we're saying is we're creating that I outside. That way it'll persist after the loop is over. And that'll be useful for us in a minute. All right, so taking a look. We have basically this huge for loop. So this for loop is going to loop along, right, and basically explore the different indices in my hash table, right, or in my array that stores the hash table. So I, right, is basically some position like this. It's like, okay, I is going to start over here. And starting in a position that's defined by the result of the hash function, right, or the hash method. So the hash method is basically the thing, right, that encapsulates, getting the hash code, doing the modulus, and doing the AND on it. It's the actual index, right? So initially, it's like we're going to start at this index. This is where the thing wants to go. And so then basically we're going to do this check here. I'm going to say, okay, Well, this is not null, right? So while we're not looking at an empty space, do stuff inside, right? Because if I want to add something, right, I need to basically find, I have either two cases for adding. I either need to find an empty space because it doesn't exist, or it already is there, and I need to see if it's something that I should update, right? Because if I do a put on something that's already there, I should update the value that's associated with that key that, I was already in there. So initially, right, basically I'm looping as long as I don't see anything that is empty. And when I'm looping, right, this is basically me moving along one by one, right? So it's like here I'm doing, plus one, plus one, plus one. I'm moving up I one at a time, right? To basically I'm moving up I one at a time, so that basically they can have the effect of starting here, right, at the index it wants to go, and then moving to the right one slot each time, right? And checking, am I at a place that I want to add to? All right. So this loop runs, right? And two things can happen. Either I could be adding something to a table and it already exists, or maybe adding something to a table and it doesn't exist. So let's say it does exist. If it does exist, then at some point this thing in here will be true. So we'll be looking at different keys, right? We're using I to pan along and look at these different spaces within inside of our array. And at some point, right, I is going to happen upon the slot that stores the key that matches the key that we're looking for. So in that case, right, I'm going to do equals, and equals is going to compare the key that I have coming in as a parameter with the key that I have in the array. Let's say they're equal. All of a sudden I need to update value. So I update value over here and then return out. So that basically, right, kind of does everything that I need to in terms of updating something that's already there. And I can actually segment this code a little bit. So let's say this over here is basically, so this is resize. This is update, right, existing one. And this over here, which you're going to go to, I should actually include the last line. This is add new. And I suppose these lines over here, if I were to label them as something, these lines over here would be explore, right? Those are exploring my my different indices. So yeah, so let's say, right, we pan through the whole thing, we don't find what we're looking for, we get to an end, we get to a null, that means that's the end of the loop exits, jumps out, what happens next? Then we jump down to this add new block at the end. So keys of I equal key, values of I equal value, and then n++. Basically that's adding that key value pair to the index we're currently looking at, and then incrementing n, right, to move forward one more step. So yeah. Those are kind of our two different cases there, right? And that will support us, adding a new element to this array. Okay, so that's how put works. Let's see, what do we got? Now we also got get. Get is basically the same thing, but it's a little bit different, right? Because it doesn't need to worry about the case of adding a new element, right? I can basically just search for stuff. So again, we have some similar code. Here again is basically our explore code. So our explore code, this basically needs to match this over here, right? These have to be the same. Right? If I want to look for something, right, I need to basically have this agreement between, this is where I'm going to put it, this is where I'm going to look for it, right? Those things have to be in agreement, otherwise I'm going to end up putting something where it can't be found or looking for something where it won't be. So those two things have to be identical. All right, so let's say we have that. Inside we basically just have an if statement. Do the keys match or not, right? Are they equal? If they are, return the value, right? So we basically look through, right, each slot. We already talked through this, right? Look through each of these one at a time. Maybe we hit it. If we do, return the value. Otherwise, the loop ends and we're basically done, because what that implies is that we can't find what we're looking for. So just return null to indicate back to the outside that there isn't anything, in this array, right? We weren't able to find, the key that we were looking for. Just return null. All right, so that's get. The last function we need to talk about is resize. Okay, so resize is here, and it's a little bit hacky. So and you'll see what I mean by hacky in a second. So resize, right, is basically the thing that says, okay, you know what? You have an array of size this, and if you want to double it, I can help you, right? If I want to make this thing bigger, I can help you out with that. So what does it look like? Well, first step is, inside of resize, it creates a new linear probing hash table, but of the bigger size, right? So notice that this argument here is cap. So it's like, well, resize is told it wants to make something that's 10,000, so now it's going to actually build itself a brand new linear probing table of that size of 10,000 or whatever. So it's a little bit kind of hacky there, because all of a sudden it's like you're not really updating the one you're working on, you're building a new one. So you build a new one, right? Initially it's empty, and what you do is you basically just loop along all the keys that you have, right? Everything that you are storing, the original hash table, and then, right, pull out everything and add it to the new one, right? So we're looping along, right? This loop over here is basically looping along everything from 0 to m, right? Basically the entire linked to that array inside, looks at every element. If the elements aren't null, right, meaning there's something actually being stored there, it takes them out, the value in the key, and puts them into the brand new hash table that it just built of the larger size. So it does that, basically builds this thing from scratch. And then what we do is we basically cheat. And we say, you know what? We're going to go to this new hash table we just built, and we're going to borrow the keys array, borrow the values array, and borrow their emma value. Okay, and we'll just do these as assignments, right? So it's like, well, all of a sudden, you know, I initially write with some object, and I contain this array, and then I built a new object that contains this array. Basically, what I'm saying is, you know, forget about this, just use this one instead, right? Because here it's like I'm forgetting about my keys. I'm taking the keys from the temporary one that I just built, right? That's what T stands for, the temp. Same thing for values. Same thing for M. So yeah, we resize. We don't really implement it. We just say build a new hash table, populate it, and then borrow the array that they set up. All right. So final thing for you guys. Just one last question for some understanding. How hard would it be to implement delete for a How hard would it be to implement delete for a linear probing based hash table? What do you guys think? So delete is a little tricky, and the reason is the following. So let's say we have an array like this, and let's say we have some spaces in here, and let's say this is index 0, and you know, for some reason, right, all these are filled up. And when I go to add a 0, it goes over here. Now suppose, right, and let's say I'm inserting, this is a 0 over here I inserted, and then let's say, right, that this is maybe something like a 1 over here, right? Maybe there was a 1 over here, or yeah, let's say there's a 1 over here. So imagine you have that configuration, right? So on and so forth. And really, right, our 0 wanted to go and be put in that first position. So let's say that's how the world works. Let's suppose I do delete on 1. Well, if 1 goes away, then I have a null space there. But the problem is, if I now go and say search for 0, well, that loop will actually run, right? You picture that loop as like starts here and walks along this. It basically sees a null space and says, oh, hey, if I see a null, that means that this thing doesn't actually exist, right? It's not going to actually go and look for the 0, right? Once you see your first null, that's actually the algorithm's key to insert that value and key, into that null space, because you want to put it, right, as close to the starting point as you can possibly be, right? You want to go into index 0, so you want to have it added to the index that's close to that. But again, the problem is here, that index that is next to the 0 position, right, where it wants to go, it was occupied by 1. We just deleted 1, and the actual 0 is over here. And instead, right, we might go and basically insert something here or return null and say it doesn't exist. And so the problem is, right, is that somehow when we added 1, right, when one was in this array, the existence of 1 impacted where 0 ended up, right? If 1 hadn't existed, then 0 would have ended up over here, right? But because 1 was there, it was a full spot, and we just kept on looking, where is the free space? Oh, the free space is over here, and so 0 ended up over here. And so basically the problem with delete is that everything downstream needs to be changed. So it's like, well, I made a space here, so it's like, well, if 0 wanted to go there, right, 0 should be able to move it up, right? And really what I need to check is I need to check everything. So everything to the right-hand side over here, I need to check it and see if anything wants to move to the left, right, to occupy that space. So everything basically that's in the probe sequence for the index, right, I need to potentially update, I need to potentially move to the left. So delete is a little bit of work. All right. So at this point, we've kind of gone over all the major methods inside of this class. Hopefully you have a better understanding now basically of the Java implementation of this data structure.